This lecture is on pH and pOH in acids, bases, and water. From the Bronsted-Lowry theory, water can self-ionize to form the following reaction. Here, one water molecule acts as a base and attracts an H+ ion from another water molecule acting as an acid, resulting in the formation of HCO+ and OH-. The end result is that the ion product constant, or Kw, equals the product of HCO+ and OH- concentration, equaling 1.0 times 10 to the minus 14 at 25 Celsius units. Kw is temperature dependent, meaning that as temperature increases, Kw's value increases. In conclusion, if HCO+'s concentration is greater than OH- concentration, it is an acidic solution. If HCO+'s concentration is less than OH- concentration, it is a basic solution. If HCO+'s concentration is equal to OH- concentration, it is a neutral solution. Using the ion product constant equation, one can solve for HCO+'s concentration by taking the Kw value and dividing it by the concentration of OH-. One can solve for OH- concentration by taking the Kw value and dividing it by the concentration of HCO+. pH measures the acidity of a solution, and pOH measures the basicity of a solution. pH equals the negative log of HCO+'s concentration. pOH equals the negative log of OH- concentration. At 25 Celsius units, pH plus pOH equals 14.00. Here to the left is a pH and pOH table showing the ranges for when it is acidic, and for pH, it is when it falls from 0 to 7, or from the pOH scale when it falls between 7 to 14. The pH for a neutral solution is when it equals pOH or 7. The pH for a basic solution is when it falls between 7 to 14, or pOH falls from 0 to 7. On the right are some examples of everyday items that are acidic and basic substances. In conclusion, a solution is acidic if HCO+'s concentration is greater than OH- concentration, pH is less than 7, or pOH is greater than 7. A solution is basic if the concentration of HCO+ is less than OH- concentration, pH is greater than 7, or pOH is less than 7. A solution is neutral if the concentration of HCO+ equals OH- concentration, or pH equals pOH, which is 7. Problem 1 is, suppose you have a solution whose HCO+ concentration equals 0.0200 molar. What is the pH of the solution? The answer is pH equals negative log of 0.0200 equals 1.699. Since the molarity has 3 sig figs, that is how many digits it is to be expressed after decimal value. Shown to the right is how one can perform this calculation on a scientific calculator. One can determine HCO+ and OH- concentration by taking the antilog of pH and pOH respectively. HCO+'s concentration equals 10 to the minus pH, and OH- concentration equals 10 to the minus pOH. Problem 2 is, if the pH of a solution is 4.33, What is the H3O plus's concentration of this solution? The answer is 10 to the minus 4.33, or 4.7 times 10 to the minus 5 molar. There are 2 digits in the pH after the placeholder, so the molarity is expressed to 2 digits. Shown to the right is how one can perform this calculation on a scientific calculator. This figure shows overall all of the calculations mentioned in this lecture relating to H plus's concentration, OH minus's concentration, pH, and pOH by its respective formula. Here is a review exercise for you to do. Suppose you have a solution whose pH equals 4.55. Is this solution acidic or basic? Determine the pOH, OH minus's concentration, and H3O plus's concentration. For the remaining part of this lecture are solutions to review exercises or problems. Please view only after completing these exercises.